In this question, we will be dealing with the approximate equivalent circuit of an induction motor. So what do we have? Here is the nameplate rating: 460 volt, 25 horsepower, 60 hertz, 4-pole machine. And so we can see that this is FE, and we have 4-pole machine. They have given the characteristics of the approximate equivalent circuit. If we know the values of the impedances, and then we have the total rotational losses they have given us. This is actually the mechanical losses, and they have also introduced this thing that the core losses have been lumped up with the rotational losses. So for a rotor slip off, they have given us a slip as 2.2%, and this will be 0.022. And we have to find the characteristics. So the first characteristic that they require is the speed of the motor. So to find the speed of the motor, and we know that this will mean the mechanical speed of the motor, first we need to calculate the synchronous speed, and we know that the synchronous speed is actually 120 FE over P. So in this scenario, FE we have 60 hertz, number of poles we have 4. So the synchronous speed of the motor inside the motor, and synchronous speed is actually the speed of the rotating magnetic field. It is 1800 rpm. Now to calculate the mechanical speed we know is actually 1 minus S into N synchronous. Slip we have now calculated, it is 2.2% or 0.22. Synchronous speed we have already calculated. So the mechanical speed of the motor will turn out to be 1760 rpm. Okay, the next part is saying we have to calculate the stator current. So what is the stator current in our machine? Stator current is actually, if you look at the circuit diagram, this part is being represented by the rotor, and this part is the representation of our stator. So the current that they want is this is I1 is the stator current. And if we know how this circuit diagram is produced, there is the logic that our induction motor is a rotating transformer, and then we find out the circuit very similar to the circuit that we have studied for transformer for an induction motor, and then we reflected the rotor side towards the stator side, and by multiplying the turns ratio and all the critical impedances, the final approximate equivalent circuit was as it is shown in the diagram. Now the question to calculate the stator current becomes very straightforward, as this is a simple question of series parallel RL circuit, as we have done in fundamental electronic courses. By what that I mean is, if I am able to calculate the resultant impedance, if I am able to solve this and calculate the resultant impedance for this thing, ZT, then I know what is V phase. I can calculate V phase. They have given to me 460 volts. 460 volts is line to line voltage, but I can convert it into phase voltage. I can easily calculate I1. So one of the tricky part or the lengthy part you can say will be how to calculate the total impedance. So in this scenario, what happens is these two resistances are in series. So we will find out one impedance for this thing. These are two parallel. For example, this circuit we have this is one impedance and this. So what we will do is we will calculate one impedance by multiplying they are in parallel, so I call this maybe ZF, and I will calculate these two are in series, so I will call this Z2. Now once I have these two, they are in parallel, so I will calculate their impedance in parallel. It will turn out to be an impedance, one impedance, then it will add with this already existing impedance in series. So finally we will have one impedance ZT, and this now we will divide by V phase by this ZT, and we can calculate I1. So I will perform, and I hope it will become clear. So so first let's look at these two, and we add them. They are in series, and for the Z2, this is actually R2 divided by S plus JX2, and the value of R2, we know that it is already given. Here are all the critical values that are given to us. So slip, we know that it is 0.022. The value of R2 which is given is 0.332, and X2 is 0.464. So when we solve this, the value we will get for Z of 2 is 15.1 with the angle 1.76 degrees. This will be Z of 2. Now let's look at the magnetization branch, this branch, and both of them are in parallel. So let's call this, this was 1, and I call this ZF, and Z of F is actually, if you look at them, RC into JXM divided by RC plus JXM. Or you can convert them to admittances, and you can solve them with all the things. The value of RC and XM is given to us. Here is 26.3. We have, so in this circuit actually this is the approximate equivalent circuit, but they have not mentioned RC, and they have only mentioned X of M. So this means that RC, the value of RC is so large that we can assume that this is open circuit. This does not exist, and only we have Jx of M in parallel. So this would actually become, and we have calculated Z2, and actually Z2 is this, we have calculated Z of 2. Z2 is in parallel with Jx of M. They both become parallel. And how I have calculated Z2? I have added these two impedances. So actually this will become, I call this Z of F, and this will actually become Jx of M into Z of 2 divided by Z of 2 plus Jx of M, because they are two parallel impedances. And when we solve them, we have the value of Jx of M, Z of 2 we have calculated, and the value of this will become Z of F will become 12.94 with angle 31.1 ohms. So what happens is, what is Z of F? Z of F is, we have first combined them, this does not exist, then we have solved these two. So finally what we get is, after solving all this circuit, we have one impedance for all of this, and that is called Z of F. This is known as Z of F, the equivalent of this part. And this Z of F actually comes in series with this impedance, that is, we call it Z stator, is in series with Z of F. So the third impedance would become Z or I can say Z total is actually Z stator, that is R1 plus JX1 plus Z of F. So this is actually R1 plus JX1 and Z of F we have already calculated here. And when we solve these, we shall be getting the value of 14.07 with an angle 33.6 degrees. Yes, here we have Z of t. So the question that we are trying to solve is we have to calculate I1. So what is I1 now? I1 is actually V phase over Z of t. Now what is V phase? V phase is actually the voltage. It is Y connected motor, so the voltage they have given, I divided by under root 3, I get V phase, that is actually 266 with angle 0, and Z of t I have already calculated. So the value of I1 will become I1 equals to, and after solving this, 18.88 amperes minus 33.6 degrees. So this is actually the current that is being drawn. So what is this current? The circuit that we have solved here is actually representing a motor which is rotating at 1760 rpm, and it was connected to a three-phase supply. So the current that is entering the machine is I1. So we have calculated this current I1 by using the equivalent circuit of this motor, which is actually given here. Now let's look at part 4. Part C. Part C says we have to calculate the power factor. So let's look at the power factor. What will be the power factor for the motor? Power factor, of course, it's the angle between the phase voltage and the current. So the power factor, we have 33.6. The current has a negative sign, so this already means it is a lagging load. And for the calculate the power factor, it will be cos theta, where theta is theta v minus theta I, that becomes 33.6 degrees. So the power factor of the motor will become 0.833 lagging. This is the power factor of the motor. Good students. So the next question is related to part D, and it states that let's calculate power converted and power output. So to get this area, we should remember what the power flow diagram of an induction motor looks like. We know that we have the input power, and we have stator copper losses, and then we have core losses. After that, the power is converted, it is the air gap power. Then we have rotor copper losses, and then we get the power converted. That means the electrical power is now converted to the mechanical power. So in this question, they have already mentioned that the core losses of the motor are coupled with the mechanical losses or the rotational losses. So let's see that yes, we can calculate input power. We have the line current, that is the stator current we calculated. There is the terminal voltage, we have the power factor, we can calculate input power. Now can we calculate stator copper losses? Yes, we can calculate stator copper losses because we have the stator current and we also know the resistance of the stator. Then so we can easily find out air gap power for our motor. Now to find the converted power, there is this formula, the P converted, or we can see the P mechanical power, the electrical power converted to the mechanical power is actually 1 minus S air gap power. So if we have the air gap power and we know the slip, we can calculate the converted power, and from the converted power, if we minus our rotational losses, we will be able to get the output power. So let's see how this is working. So what I have briefly told you, if this is the power flow, so what is be happening, we will be having P in here, and from P in, if we remove the stator copper losses, we will have our air gap power. And once we have our air gap power, we are able to calculate from the air gap power. There are rotor copper losses, but we are not given with the rotor copper losses, but they have given us slip, so we are able to calculate P converted, and from P converted we will then subtract our rotational losses, that are the mechanical losses. Now rotor losses and rotational losses are different. Rotor losses we are calculating by the help of the formula containing slip. We are compensating that one. Rotational copper losses are the mechanical losses, and after we subtract this, we will be having P out. So they are actually they required the converted power, this power, and this power is required in this part. So let's start solving this. The first step would be, let's change the color. The first step would be to calculate P input power, that is under root 3 Vt I of L cos of theta, and we know that this is 460 I line, IL line that we have calculated, that is stator current, and cos of theta is 0.833. So the input power to the motor will become P input equals to 12,530 watts. This is the one. After that, as I told you, we have to calculate stator copper losses. We have calculated this thing. So stator copper losses are actually I1 square, as it is this is three phase power for 3, I1 square into R1. What is meant by here? The power being lost here. These are stator copper losses for our motor. And for 3 phase, it we multiplied by 3, I1 square, I1 we have calculated, R1 it's given. So stator copper losses will become 685 watts. So when we have this value, so the air gap power, the power at this point will become, we can calculate P air gap is actually equals to P in minus stator copper losses, and this will P air gap will become 11,845 watts. Now once we have the air gap power, we have the air gap power, and we have to find out the power converted. We know the power converted to the mechanical power. The formula for that power will be 1 minus S P air gap. So this we know is 0.022, and air gap power we have already calculated. So the converted power will become 11,585 watts. So this is actually the first thing they required. And now we have to find out, we have calculated this, we have to find out P out. So to find out, we have to, these are the mechanical losses, and core losses are lumped here. So to calculate P out, we have P converted minus P rotational losses, the mechanical losses. Rotational losses, it's given in the question. Here they have given, yes, this 1100 watts, and So the value of P out would become, P out is 10,485 watts. So this is the output of the machine. The next question, next part, they say let's calculate the induced torque and the load torque. So to calculate the induced torque in the given machine, we have to calculate the induced torque. So the induced torque is, so here actually, so induced torque is when through the air power, through the air gap, the electric flux is induced on the rotor. So the induced torque for the motor can be calculated by considering the air gap power divided by, and what is the speed of rotating magnetic field. So there, here we have the synchronous speed, but please remember that here we are using omega, that is a radians per second. So this will become this air gap power we have already calculated, which was 11,845, and synchronous machine is 1800 rpm into 2 pi over 60. This gives us in radians per second. So the induced torque will then become, torque induced is 62.8 Newton meters. This is actually at the point of power, but the most important of the torque is the output torque. The output torque, the formula for output torque is P out divided by the mechanical speed, and P out we know we have calculated 10,485, and mechanical speed is 1710. Then we convert it into radians per second, and the output torque for the motor is 56.9 Newton meters. And the last part is about the efficiency. Efficiency we know is P out over P in into 100%. So this is simple. We have calculated the output power, and the input power for the motor is 12,530 into 100%, and this will, the efficiency will become 83.7% for the induction motor. So that's how this question will be solved. It is a relatively lengthier question. I hope it helps.